All right, welcome everyone. Go ahead and grab your notebooks and get settled in. I am so thrilled you're joining me for this Ultimate Explainer crash course in nuclear physics. For the next few minutes, consider me your personal professor. My goal today isn't just to help you memorize a bunch of facts, but to completely demystify the incredibly powerful, microscopic engine that essentially runs our entire universe, all so you can confidently ace your upcoming exam.
Here's our game plan for today. We're going to start with the anatomy of the atom, then move into categorizing the core, followed by binding energy and forces. After that, we'll tackle radioactivity and decay, and finally, we'll wrap it all up with the heavy hitters, fission versus fusion.
Okay, let's dive right into Section 1, Anatomy of the Atom, Setting the Scale.
To really wrap our heads around the mind-bending scale of an atom, you gotta realize something crazy. It is almost entirely empty space. The nucleus is actually 10,000 times smaller in radius than the whole atom itself, yet miraculously, it contains over 99.9% of the total mass. To make this stick for your exam, just think of the classroom analogy. If you magically blew up an atom to the size of a giant university lecture hall, the nucleus, which literally carries almost all the weight, would be the size of a single tiny pinhead resting perfectly in the exact center of the room. The rest of that huge space? Just the electron cloud. It is profoundly empty.
Moving on to Section 2, Categorizing the Core, the Rule of Three. So examiners absolutely love to test you on how we classify nuclei, which means we need to master the essential vocabulary. You gotta know these three terms cold. We're gonna use a super simple mnemonic device, PNA. Just pay close attention to the spelling here. First up, isotopes. You spot that P? That stands for the same protons. They're chemically identical, kind of like three different forms of hydrogen. Next, isotones. Check out the N. That means they share the same number of neutrons, like mercury and gold. And lastly, isobars. Focus on that A, which represents the mass number. Isobars share the same total number of nucleons, like tritium and helium-3. So just remember, PNA. Link that specific letter with the characteristic, and I promise you will never mix these up on a multiple-choice question.
All right, Section 3, binding energy and forces, the ultimate glue. Now, we've got this incredibly dense pinhead of a nucleus, right? And it's packed tightly with positive protons. But this brings us to a massive structural problem. Let me pose a little scientific mystery to you. How can a whole weigh less than the sum of its individual parts? Seriously, if you take a bunch of protons and neutrons and bind them all together, the resulting assembled nucleus actually weighs less than if you weigh them individually on a scale. I know, it seems like it completely violates basic math, right?
Well, to resolve this paradox, imagine a balance scale. On one side, we have 8 totally unbound protons and 8 unbound neutrons. On the other side, a fully assembled oxygen-16 nucleus. And guess what? The assembled side is actually lighter. So where exactly did that mass go? This is what we call the mass defect. And the resolution to this is essentially the ultimate plot twist in physics, brought to us by Albert Einstein. That missing mass isn't just gone. It's literally been converted into the exact binding energy required to hold that incredibly dense nucleus together. That's your E equals mc squared in action. Basically, to hold the atom together, the universe demands a toll, and that toll is paid in mass.
So that mass becomes energy, specifically manifesting as the strong nuclear force. When you map out the relationship between potential energy and distance, understanding that curve is absolutely vital. There's a deep dip where the force becomes strongly attractive, completely overpowering the intense electromagnetic repulsion of all those positive protons. But notice how quickly that attraction flatlines and drops to zero as you move away? This force is strictly short-ranged. I like to think of this using a Velcro on a packed subway analogy. The strong force is incredibly powerful, like industrial-strength Velcro, but it only sticks to the individual nucleons directly touching it in the crowd. It doesn't care at all about the protons on the opposite side of the nucleus. Oh, and if they get too close, like below 0.8 femtometers, the force abruptly shoots straight up, meaning they strongly repel each other. That's what prevents the whole nucleus from just collapsing in on itself.
Building on that, let's talk about arguably the most crucial concept in all of nuclear physics, the arc of stability. Seriously, if you only remember one concept from our explainer today, make it this one. When we map out the average binding energy per nucleon, the higher up you go, the more stable the nucleus is. So the absolute summit, right there, peaking in the middle, is iron 56. It is the most tightly bound, stable configuration of matter in the entire universe. Honestly, everything just wants to be iron. Light elements can actually combine or fuse to get heavier and climb up that hill toward iron, which releases massive amounts of energy. On the flip side, heavy, unstable elements can split or undergo fission, shifting back down toward iron, which also releases energy. In the end, both of these processes are really just the universe trying to roll down the hill toward ultimate stability.
Which brings us to Section 4, Radioactivity and Decay, the Quest for Balance.
Since not every nucleus gets to be iron, plenty of them are stuck in this really unstable state. You can kind of think of radioactivity as a relatable, spontaneous quest for an unstable nucleus to just finally find some balance. Basically, there are three main ways a nucleus can go on a diet to reach stability, and you absolutely must know the differences between them for your test. First, there's alpha decay. This is all about shedding bulk mass quickly. The nucleus basically chucks out a heavy helium nucleus. That's 2 protons and 2 neutrons. Second is beta decay. This one's more of an internal adjustment. The nucleus swaps a neutron for a proton or vice versa and spits out an electron or positron in the process just to fix its internal ratio. Finally, gamma decay. Now this one changes no particles at all. The nucleus is just way too overexcited and needs to shed pure energy, which it does by firing off high-energy electromagnetic photons. So just remember, alpha is for bulk, beta is for ratio, and gamma is for pure energy.
All right, Section 5, Fission versus Fusion, Reactions and Resolutions.
We are officially in the final stretch. Let's compare the massive energetic processes that power our terrestrial reactors and the stars themselves, starting with the exact mechanics of nuclear fission. Imagine a uranium-235 nucleus. Step 1, a slow-moving neutron approaches, and it actually has to be slow so it can be captured. Step 2, the nucleus absorbs that neutron, instantly becoming highly unstable uranium-236. Step 3, it literally can't hold itself together. It violently fractures into intermediate fragments, releasing 3 stray high-speed neutrons and an astounding 200 mega-electron volts of kinetic energy. Those fragments fly apart, generating a massive amount of heat. This exact 3-step dance is the fundamental mechanism powering every single modern nuclear reactor on Earth.
Now, let's look at the complete opposite process, fusion. The core challenge of fusion is basically overcoming a massive hurdle known as the Coulomb barrier. 2 positively charged nuclei naturally want to repel each other intensely, so for them to fuse, they have to get close enough for that short-range, Velcro-like strong nuclear force to take over. But how do you push them past that barrier? Well, you need extreme kinetic energy, and that is only achieved at thermonuclear temperatures of roughly 1 billion Kelvin. You literally have to turn the fuel into a volatile, high-energy plasma just to force them together. To really solidify this for the exam, let's contrast these 2 supreme energy reactions side by side. Fission is splitting heavy, unstable nuclei, like uranium or plutonium, using slow neutrons. Fusion, on the other hand, is joining light nuclei together like deuterium and tritium, which requires extreme heat and plasma confinement. Fission yields a ton of energy, about 200 MeV per massive nucleus, but fusion yields vastly more energy per unit of fuel mass. Essentially, fission is what we do here on Earth, fusion is what happens naturally right in the interior of stars.
And this brings our structured review to its grand conclusion. On one hand, we have the microscopic mass defect holding a single tiny nucleus together. On the other hand, we have the vast cosmic scale of thermonuclear fusion powering a star. Whether it's the intense heat inside a terrestrial reactor or the stellar engine of our sun, it is all governed by one single, unified law. It's the continuous, incredibly elegant interconversion of mass and energy dictated by Einstein's E = mc squared. So I'm going to leave you with this final thought as you prep for your test. Are you ready to look up at the sun's warmth and then look down at a nuclear power plant and recognize that they are being driven by the exact same beautiful equation? Review your mnemonic devices, keep that curve of stability in mind, and you are absolutely going to crush this exam. Thanks for joining me on this explainer today. Class dismissed.